Welcome to this lecture series in real analysis. This is our first lecture, and in this lecture we'll be looking at the formal construction of rational numbers arising out of integers. So what we need to know is basically what are natural numbers. I'm sure you've learnt about them in high school. They are all the counting numbers, as they are called sometimes. So that is the set of natural numbers, and one can add them, multiply them, take difference, but the difference of two natural numbers may not be a natural number, and so on. And we also need to know about the set of all the integers. So this is the notation for the set of all the integers, which is an extension of natural numbers. It includes what are called negative numbers as well as the number 0. And there is also an arithmetic on them. You can add or subtract them or multiply them. Once you quote-unquote divide two integers, then you may not necessarily get an integer. So the point is that the set of rational numbers, as we again learned in high school, is supposed to be all the ratios of two integers, whatever ratio means. So the point of this lecture is to formalize what is the set of rational numbers and the algebra on them. And we need to know about relations to make that construction. Especially we need to know about equivalence relations. So in this playlist, I have included things about sets, functions, and relations, and some more things. There is a playlist named Kickstart in which many more such primers are available. Both those links are in the description below. So please refer to those lectures, and with that we can continue. So how do we construct rational numbers? Okay, so we start again with Z. Z is the set of all the integers. Let me repeat. Okay, so consider the set S, and before I continue, let me say that what we are going to discuss is a very, very formal way to look at rational numbers. That is not how we think of rational numbers. We think of rational numbers the way we think of them in high school. But the point of this lecture is to put them on a firm logical foundation. Once you are tasked with explaining what is a rational number, you may be able to offer intuitive ideas, but the formal construction is a little bit more ruthless. The reason for doing this is that we want to answer the question, what are real numbers? That is actually a very difficult question. We will answer that question. But in the meantime, you can think about how would you convey to someone what are real numbers? What is there in your head? And if you haven't seen a formal construction of real numbers or what are real numbers in any formal capacity, then I would think that you would struggle with answering that question, because many, many mathematicians did. It was actually pretty late, I think in the 19th century, late 19th century, that we finally had a proper definition. Anyway, let's continue. So what is the set of rational numbers? So first, define the set S as all the pairs that one can form of the following sort, where A is an integer and B is a non-zero integer. So this is the set of all the pairs of integers where the second one is non-zero. So that's our set S, and now we define a relation on it. So define a relation tilde on S as we write A tilde B. Wait a second. We write A tilde B if and only if. Sorry, what am I writing? We write A comma B tilde C comma D if and only if. Or rather, let me write X comma Y, it's better. If and only if AY equals BX. Right, this is our definition. This is the definition of tilde, and we claim, or I would like you to check, that tilde is reflexive. and tilde is symmetric, and tilde is transitive. So if you know about equivalence relations, which I assume you do, you would face no trouble checking all this. But let me write one line about each of them. So reflexivity asks you to check that a comma b tilde a comma b for all a comma b in S. But this is of course equivalent to checking ab equals ab, or ba if you want to write it that way, but of course that is true. So reflexivity follows, symmetry is trivial, and transitivity will require one line of computation. So let me leave this as an exercise. And therefore, tilde is an equivalence relation. Thus, tilde is an equivalence relation. Okay. So the equivalence class of the pair a comma b will be denoted as a by b, or this way. So either you write that way or this way, it's the same thing, and this should already remind us of the rational numbers as we are used to them in high school. This is how rational numbers look when we read about them in high school. Okay. So we define Q, which is Q with a small decoration, as this set, which is of course the set of all the equivalence classes. So this notation stands for the set of all the equivalence classes of tilde. Okay, so that is the set of all the rational numbers. And if you think about it, this equivalence relation, what is it trying to capture? Suppose I have this rational number, 2 by 3. It is by definition the equivalence class of this ordered pair, and equivalence class I'm denoting by putting square brackets around. So this is the equivalence class of that, which we are writing like this. But in high school, we know that 2 by 3 is the same as 4 by 6. But it is indeed true that the equivalence class of 4 by 6 is same as the equivalence class of 2 by 3, because 2 by 3 is related to 2 comma 3 is related to 4 comma 6 under tilde, right? 2 comma 3 related to 4 comma 6. Just note that this equation holds. And that is exactly what we actually do in high school. When we say that 2 by 3 is equal to 4 by 6, we just mean that 2 into 6 is equal to 4 into 3. So it is a somewhat convoluted looking way of doing what we do in high school, but this is completely formal. That's the point. This is completely logically consistent. Okay, so that's the set of all the rational numbers. And now we need to define some arithmetic on them. Addition and multiplication mainly. Let's add a page. Arithmetic or algebra, I don't want to distinguish. Algebra on Q. So we need to prescribe how to add rational numbers and how to multiply them. Okay. So let alpha is equal to a by b and beta is equal to c by d. Or maybe let alpha and beta be rationals. We define alpha plus beta as follows. So say alpha is equal to a by b and beta is equal to C by D. Then alpha plus beta is defined as AD plus BC upon BD. So that's our definition of alpha plus beta, not B. Right, that's how we define it. So it is the equivalence class of the pair whose first entry is this and second entry is that. And this makes sense because B and D are non-zero and hence BD is non-zero. So this is a legitimate equivalence class. But one can raise an objection. There is no unique representation of alpha as A by B because A by B can be equal to A prime by B prime. For instance, A by B is same as 2A by 2B. So what if we use some other representation and use that to add alpha and beta? What I'm saying is, to add alpha and beta or to define the addition of alpha and beta, we first took a representation of alpha and beta using in some way, and then used that representation to define the addition. In a different representations, these numbers would be different, and then it is unclear if you would get the same equivalence class. But you do actually get the same equivalence class. So say alpha is also equal to A prime by B prime. That is, AB prime is equal to BA prime. Right? Alpha is A by B, but if alpha is also equal to A prime by B prime, that just means that A comma B and A prime comma B prime are in the same equivalence class, which means that this is the case. So suppose this is given. Is it true that, and say beta is C prime by D prime? That is, CD prime is equal to DC prime. So then, what about this guy? Then this thing, A prime D prime plus B prime C prime by B prime D prime. We would report this as the addition of alpha and beta, but we just need to check that actually this is equal to that, which is to say that this comma that and this comma that are in the same equivalence class. And that's just a matter of computation because one can, using these equations, one can just check that this multiplied by that is equal to this multiplied by that. And therefore, addition is well defined. Even though we are defining the addition using representatives of the equivalence class, the addition is well defined. And this is no mystery because this is exactly how we add rational numbers in high school. Well, we take the LCM, but doesn't matter. You just need to have some common denominator. So this is completely fine. Right, so we are just repeating high school mathematics, but in a more formal way. Similarly, we define multiplication. So define alpha times beta as, this is much simpler. Say alpha is again A by B and beta is C by D. Then alpha beta is declared to be AC by BD. And again, one needs to check the well-definedness, but that's even easier in this case. All right, so this is how we add and multiply rational numbers. Maybe, yeah, not maybe. Okay, fine. I mean, I think this is good enough. So here are some properties of rational numbers that I want you to check. So suppose x, y, z are three rational numbers. We were using Greek letters in the previous slide, but here I'm resorting to usual things. So say these three are rational numbers. Then whether you add the last two and then add the result to the first one, or you add the first two and add the result to the second one, the last one, it's the same thing, and same for multiplication. So this is a simple thing that you can check, and this is called associativity. All right. So this is an exercise. This is called commutativity. Whether you are, the order in which you add or multiply is irrelevant. So this is called commutativity. This says additive identity. So when we write the symbol 0, we mean this guy. Right? This is a legitimate rational number. This is the equivalence class of this pair. So 0 means that, and you can just check immediately that this is the case. You add it to anything, you get the same thing back. And 1 stands for this guy, the equivalence class of 1, 1. And if you multiply it with anything, you get the same thing back. So this is additive and multiplicative identity. All right. And now you have distributivity. So you multiply x with the sum of y and z is same as multiply x and y, multiply x and z, and add them. This is called distributivity. Okay. And lastly, I want to discuss the following. So for each, let me use alpha this time. So for each alpha in Q, there is a unique beta in Q such that alpha plus beta is 0. As we have already said, 0 means 0 by 1. Okay. And it is very easy to see that it exists. Basically, say if alpha is a by b, then beta equals minus a by b does the job. Right? So the existence is clear. The uniqueness is an exercise. So if you say beta prime also satisfies this equation, then you can easily show that beta is equal to beta prime. So this is a very simple fact. And similarly, for each alpha in Q, but alpha non-zero, there is a unique beta in Q such that the product is 1. Okay. So construction, or rather the existence, is very easy. Say alpha is a by b. Now since alpha is non-zero, a is non-zero. Right? Because if a were 0, then this would be equal to 0. 0 by 1, and that would be the same thing. So a is non-zero, and hence b by a makes sense. So just declare beta as b by a, and it is meaningful because a is non-zero, and that does the job. If you multiply alpha with beta, you get 1. So existence is clear and uniqueness is again an exercise. So this thing is called the additive inverse of alpha. It is additively the inverse of alpha and is denoted as minus alpha. That's the notation. And this is the multiplicative inverse of alpha. This is denoted as 1 by alpha or alpha to the minus 1. Again, these things are all high schoolish things, but we are saying them in somewhat complicated looking manner. And this property is called additive and multiplicative inverse. So additive and multiplicative inverses exist and they are unique in rational numbers. So these are some properties of Q that one needs to be familiar with. We are already familiar with them. This is how we do things in high school anyway. Okay, so that's one thing out of the way. So we have formally constructed rational numbers and done the algebra. All right. Maybe I'll note a small thing here. It's a very small fact. So note that every alpha in Q, meaning every rational number, can be written as a by b for some b greater than 0, where b greater than 0. Right? You can always write a rational number in that fashion. Why is that? Because suppose you had 2 by minus 3, that you can just write as minus 2 by 3. So that's, it's a very simple thing. All right. So now, continuing, one last thing. Just like integers extended the natural numbers, whatever you can do with natural numbers, you can do with integers. You kind of just forget about the negative ones. Similarly, rationals extend the integers. But in what sense? The way we constructed rational numbers, they seem to have nothing to do with integers. They are just some random equivalence classes of some relation. But no, that's not the case, actually. And they do contain integers in disguise. So how do we formalize that? So define the map. Phi from integers to rationals as phi of m is equal to m by 1 for all m. So that's a map from integers to rationals, of course. So check that. Phi is injective. Well, there is nothing to do here. So to check injectivity, what do you need to know? Suppose phi m were equal to phi n. We need to show that m is equal to n. But phi m is equal to phi n means m by 1 is equal to n by 1, which implies m times 1 is equal to n times 1, which implies m is equal to n. So that establishes injectivity. Also check that it respects addition. Sorry, what have I written? It respects addition. And it respects multiplication. Okay. So what is the first thing saying? The first thing saying is that as a set, it is sitting inside here. For everything in Z, there is some guy that you can find uniquely present here. But there is more. So if you want to add two integers, you can just take the images and add. And then whatever is this guy, you can again think of as an integer because it is the image of an integer. So this map phi not just identifies the integers in rationals as, point by point. The identification respects the addition. So whatever, as far as addition goes, this identification is perfect. It is just kind of changing the name. Something had a name m here, but it just gets renamed a little bit. It gets decorated a little bit, that's all. So it respects addition, and the same thing with multiplication. So it is completely transferring the arithmetic or the algebra, if you like, of Z to Q. And in that way, they extend the integers. So rationals extend integers and integers extend to natural numbers. All right, that's great. In the next lecture, we'll be looking at the ordering on rational numbers. So in high school, we were able to compare two rational numbers, which is bigger, which is smaller. So we will talk about that, and this identification also will respect the ordering. There's already an ordering in integers. This identification will respect the ordering as well. So that will be the topic of next lecture. This is enough for this one. As usual, like, comment, share, subscribe, and I will see you next time.